We're now ready to talk about gravity in a little bit more detail. And so far, when we've tried to find the force of gravity, we've used a very simple equation that Fg equals mass times g times 9.8 meters per second squared. But the question is, where did this come from specifically? We know that mass is going to be part of it, and how much mass you have affects how much gravity you'll feel when you're here on Earth, for example. But when we talk about gravity here on Earth, why is it specifically 9.8? If we were on some different planet, would it be some completely different value? And if we were very far away from this planet even, would it be some different value than 9.8? And these were the kinds of things that Isaac Newton was investigating in more detail. And he had already come up with this basic law that here on Earth we can use this concept that our force of gravity is just our mass times a special constant, 9.8. But he was looking for a more general law, because he recognized that we don't just feel gravity here on Earth, but in fact all objects that have mass exert a gravitational force on all other objects that have mass. And so you may not realize it, but you are actually feeling a gravitational attraction, even though it might be very small, to every other object with mass around you right now. It's just that these forces often end up being so tiny that we don't notice them in our everyday lives. But very large objects, like a planet, say the Earth, they experience very large amounts of gravity, and that's why we feel the effects from Earth's gravity. But let's look at the more general law that Newton was able to come up with for gravity. So now more generally, we can say that Fg, the force of gravity, is some special constant, capital G, and I'll talk about that one in a moment. But then we have m1 and m2. And so those two values are just two masses, two different mass of objects. So those are just two masses of objects. And then we divide by something called r squared. And r is just the distance that separates their centers. So if the two objects were, say, a person and the planet Earth, then that r value would be how far away that person is from the center of planet Earth. And this was the law that Newton discovered. Essentially what this law is saying, if we break it down in a little more detail, is all about proportions. So Newton discovered that your force of gravity is going to be directly proportional to both of the masses involved. And so regardless of which object we're talking about, if either of the masses of the two objects close to each other increases their mass, that will increase the amount of force between them. But he also found an opposite relationship with how far apart they were. He found that there was an inverse proportionality, an inverse relationship between force of gravity and the distance of separation. Specifically, as the distance that separates them grows, well, it would be on the bottom of this equation. And so it would actually make the force of gravity decrease. And it's actually not just that it's inversely proportional to that radius. He actually found, through a little bit of extra mathematical detail, that it's inversely proportional to the squared distance between the centers. So we take that r value and we actually square it, and that fits into our equation nicely. And so what he discovered is that the force of gravity overall is proportional to this relationship, directly proportional to the two masses, but inversely proportional to the square of the radius. That's what his law initially said. But he realized that to take this law from just proportions to a full equation, he actually also needed to multiply by one additional value. And that's this extra value of capital G. And so this extra constant value is just one specific number that helps the two sides of the equation not only be proportional to one another, but actually be equivalent, to actually equal the same amount, the same value. And it also helps the units to work out to the correct units as well. And it's this very tiny number, actually, 6.67 times 10 to the negative 11. And then it's got a very fancy unit that we're going to talk about as we go through unit analysis. And so it's a very tiny number, and it multiplies everything else in the equation by that very tiny number. And that's part of the reason why average size objects experience very tiny amounts of gravitational force between one another. It's only when we have a very large object, like I said, a planet, that we really notice these gravitational effects acting on larger sized objects. So if we do a little bit of unit analysis, we can use that to understand why the unit for capital G, our new gravitational constant, why it has such weird units. And if you take a look at the units, it's Newton meters squared per kilogram squared, and we want to understand why that is. Well, let's think about what we're trying to get. We know that in our answer, we are measuring a force of gravity, so we need our answer to be in newtons. And then we're multiplying a few things together on top. So we're multiplying, and I'm just going to put all this multiplying stuff in a bracket. We're multiplying our value G, and I'll explain that unit in just a moment. But we also know that we need to multiply by kilograms, and then kilograms again, because we've got two masses on top. And then we take all of that and we divide by something that's in meters, but then those meters are being squared. We're, remember, dividing by the square of the distance of separation. So the only unit that I haven't filled in yet is this special unit for the gravitational constant. So why did it end up being such a weird unit? Well, when I write that unit in, specifically, once again, remember it's Newton meters squared per kilogram squared, that has a very interesting effect. First of all, this kilogram squared helps to cancel out both of the two powers of kilograms that are on top of that fraction. On the top of this unit, we have a meter squared, which is canceled out when we eventually divide by meters squared. And so all of the units end up canceling out except for the unit of newtons, which is what we wanted in our final answer anyways. And so all you really need to understand is that this gravitational constant, big G, has the very weird unit only for the purpose to make all of the other units work out and make sense and fit together to produce newtons. And now we can actually try and use this formula to help us figure out some forces of gravity. But again, remember, we're not just concerned with how much gravity something's feeling from the Earth. We're now interested in how much gravity any object is exerting on any other object. So, for example, if we just have two regular people, who we'll call Alice and Bob, and they're sitting beside each other, and we know Alice's weight, and we know Bob's mass in kilograms, we know how far apart they're separated, and we know that anything with mass feels a force of gravity. So we're trying to figure out what is the force of gravity that they feel between them. So let's write down some things that we know. Well, for Bob, we know his mass directly. So I'm going to call it M with a little b for Bob. Mass of Bob is 75 kilograms. And then we have to be really careful with Alice's situation, because I'm being a little extra tricky with you in this question. I'm not actually giving you Alice's mass. The wording, remember, says it's her weight, and you'll notice that it's given in newtons. And so what I'm actually giving you there is the number of newtons of force that Alice would feel from gravity just here on Earth. So essentially, that weight that's being given, remember, weight is a force of gravity, but I'm going to put a little bracket to my subscript, because it's the force of gravity, but it's the gravity that is felt between Alice and the Earth, or in other words, from Alice to the Earth. A to E is my way of saying that. It's the force of gravity felt between Alice and the Earth. And that force of gravity is 565 newtons. We also know that the radius, or the r of their separation, the distance that they're separated, is 0.225 meters. And in reality, we're still trying to find a force of gravity, but it's not the force of gravity that either of them feels with the Earth. It's the force of gravity that attracts them to one another. So we're going to look for Fg A to B, which is my way of saying we're looking for the force of gravity between Alice and Bob. That is really our unknown value that we're trying to find. And so we almost have everything we need to plug directly into our new formula. But we just don't have the mass of Alice yet. We have her force of gravity on Earth. So we need to take a little step to find her mass. Because remember, if we know the force of gravity between Alice and Earth, we know that more specifically it's equal to the mass of Alice multiplied by little g. And so here's the distinction you have to always make. We'll use a little g to represent 9.8, that specific amount of gravitational acceleration that things on Earth feel. But we'll use capital G, or what I'll call big G, to be the constant value that goes into this more general gravity formula, the gravity formula that we're eventually going to use when we do Alice and Bob. But remember, this original formula is still true. Specifically in our case, though, we want to know just the mass of Alice. And so it's going to be the force of gravity from A to E divided by the value G. Or in other words, it's going to be 565 newtons divided by 9.8 meters per second squared. When we do all of that, we get approximately 57.7 kilograms. So that is our approximate measurement of Alice's mass. And now that we know that, we can use our brand new formula a little more directly. Because in the end, we don't really care about how much gravity Alice is feeling on Earth. We want to know how much gravitational force is between her and Bob. So we're trying to find Fg from A to B is my way of saying that. And again, that just means the force of gravity between Alice and Bob. When that's the case, we know it's going to be our big constant value G, big G, and it's going to be the mass of Alice also multiplied by the mass of Bob and divided by the distance that they're separated squared. So let's plug in what we know. I'm going to put my equal sign over here to give me a little more room to work. I've got 6.67 times 10 to the negative 11. For these longer calculations, I'm okay if you leave out the units. 57.7 kilograms was Alice's mass, and we know that Bob was 75 kilograms. We're going to divide all of that by 0.225 squared. And our answer that we get should give you some indication as to why Alice and Bob aren't actually getting pulled towards each other, even though they're fairly close by. Because the answer we get is approximately 5.7, and I'm going to put it into scientific notation, times 10 to the negative, oopsie, not negative 11, but times 10 to the negative 6 newtons. So that is an incredibly tiny amount of force. That is why, even though in reality there are gravitational forces between you and every other object with mass around you, those amounts of gravitational force are so tiny that you won't really notice them in your everyday lives. And in fact, our bodies just naturally get used to feeling those very tiny, infinitesimal amounts of force, and our brains don't even register them anymore. They don't notice or react to them in any way. But it doesn't mean the forces aren't truly there. There are very detailed experiments that can be done when you can eliminate all of the other forces that affect these things and allow them to move very freely. Even these small amounts of force will cause any object to attract any other object with mass. So of course, for a question like that, you'd still want a final therefore statement that says, therefore, the total amount of force felt between Alice and Bob is the 5.7 times 10 to the minus 6 newtons. But I'm going to leave that for you to write in. The bottom part gets into how this new equation connects back to our old equation for gravity, that old Fg equals mg formula. Because there is a direct connection between the two. And in fact, we can show that our old formula, Fg equals mg, is just a simplified form of the bigger equation that we've now learned, that only works in a special situation. We're going to go through those details in class, though, and I'll recap all of this note and take any questions at that time.